Hi, grade 12, and welcome. It's Physical Sciences again, and I'm going to take you through a 1 hour, 15 minutes lesson as usual. And today, we're going to talk about electrochemistry. So this is the topic for today. And in electrochemistry, we want to understand right from the beginning, what is it all about? So what is this electrochemistry? What happens in here? And we have got, specific terminologies that we use in electrochemistry. That will also be looked at. We will clearly explain and define some of, or in fact, almost all of these terminologies involved in electrochemistry. We are also going to talk about the different types of electrochemical cells. And basically, the ones we're going to talk about, they are the basic two types of cells in electrochemistry called the galvanic cell and the electrolytic cell. Now, let's get into business. The first thing that we need to look at now is defining what electrochemistry is all about. Let's have a look at it. Now, electrochemistry is a study. So it's a study in chemistry where we look at chemical reactions that involve the transfer of electrons. Now, this is very important. This type of chemical reactions involve transfer of electrons. Now, in these reactions, it means that one substance, one particular chemical substance is going to lose electrons, whilst another, so when electrons are lost from one, there should be another substance that is ready to receive those electrons. So one substance loses electrons, another receives them. So this means that if we have substances A and B, so if A loses, B gains or receives those electrons. And the same electrons that A lost are the same electrons that B is going to gain. So hence we say at the bottom here that the processes, these processes of losing electrons and receiving of electrons, they occur at the same time. So you don't have a situation where a substance, just one substance, lose electrons and the electrons float into the air or fly around or looking for something to receive them. In other words, once a substance loses electrons, it means there's a substance that is waiting to receive them. If this substance that is waiting to receive the electrons was not there, then this substance was not going to lose those electrons. So the two processes occur or happens at the same time. Now that is very important for you to understand, because we can't explain losing of the electrons alone without knowing where these electrons are going. In fact, that very process of losing is triggered by the fact that there is one substance waiting to receive those electrons. Now let's move on. Let's come to the terminologies. First term that we're going to look at is a term called oxidation. Now, what is oxidation? Oxidation is a process that involves losing of electrons. So oxidation is the loss of electrons. Loss of electrons. Okay? Now we know that electrons are particles from atoms of substances that carry a negative charge. Hence we put E- to show that these electrons are substance or are particles of an atom that are negatively charged. So when a substance loses electrons, we say that substance is oxidized or it has undergone oxidation. Reduction on the other side. Reduction is the gaining of electrons. Okay? So reduction is the gaining or receiving of electrons. Okay? So when receiving of electrons happen, okay, we say reduction has occurred. Right, now that is reduction. Now let's move on and look at the next term. It's oxidizing agent. Now what will be an oxidizing agent? An oxidizing agent will be a substance. So it's a substance. It's a substance that gains or receives electrons. A substance that gains or receives electrons. Okay, so that substance is called an oxidizing agent because it causes the other substance to lose electrons. The next one is the reducing agent. Reducing agent will be a substance that loses electrons. Okay, that loses electrons. Sometimes you can define it as a substance that donates electrons. So instead of loses, you can also say that donates electrons. Okay, now this is a substance where the electrons are coming from. We call it the reducing agent. Next is a term called cathode. What is a cathode? A cathode is an electrode. Now I'll explain a lot more about electrodes as we move on in this lesson. A cathode is an electrode where reduction takes place. Okay? It's an electrode where reduction occurs or takes place. And then lastly, in our list of terms, we've got anode, and in this case, we define the anode as an electrode. So an anode is also an electrode, okay? And this type of electrode is where oxidation takes place. Okay, so anode is an electrode where oxidation takes place. Right, so that is more or less the definitions of terminologies that are involved in electrochemistry. Let's now move on, and we're now going to begin to talk about types of electrochemical cells. Now the first one we will be looking at or talk about is the galvanic cell. So we've got one type of electrochemical cells called a galvanic cell. In other words, when we talk redox reaction or reduction oxidation reactions or electrochemistry, we end up talking about these chemical cells. One of them is the galvanic cell, like I said. Next one, or the second one, is the electrolytic cell. Now, there is a diagram for an electrolytic cell. I'll explain more about these two cells as we move on. But let's quickly get back to the galvanic cell, and then we put flesh into it, because it's very important for us to understand what's happening here. Now, although things may not be looking like they are tying up at the moment, please just follow the lesson, go with me, and at the end we are going to tie all the loose ends, and you're going to see what the main issues are in this lesson. Just listen carefully, because I'm going to explain generally what a galvanic cell is all about. Okay, now if you look at this cell here, first of all, you would see we've got polarity there. So we've got minus and plus. So that tells us that we've got potential difference. Hence, we're saying there is V up there. Now, what is this cell made up of? You will see that this is the output. In other words, this is the point where we're getting the outputs of the cell. Now, this tells us that this cell is able to produce energy. In other words, electrical energy. Where does this electrical energy come from? Okay, so we see this cell producing that electrical energy. Where is the electrical energy coming from? The electrical energy is coming from these two parts here that I'm going to to explain to you further as we move on. These, you can see, these are beakers, if you like, with solutions inside, electrodes there, electrodes there. So there is some chemicals here. Okay, so we have got chemicals here, and through these chemical reactions happening here, the output is electrical energy. So we have got a situation where this cell here converts. So a galvanic cell, if you like, galvanic cell converts, it converts chemical energy into electrical energy. Chemical energy to electrical energy. Okay, so chemical energy from electrical energy, because we've got chemical reactions happening down here, and the output is an electrical energy, as we can see there. Now, let's look at the whole cell and try to label it and try to know what are all these components that are used to make a galvanic cell. First of all, I said here, if you see there's a solution here, it's actually a solution which is ionic. Now, what is an ionic solution? It's a solution with charges in it. It has got negative ions and positive ions inside there. The same way, this one, so these two here are ionic solutions. Okay? This part here is called an electrode. Remember when we were defining the terms involved in electrochemistry, we came across electrode, and this is an electrode. This electrode is usually made of a metal, okay? And we will explain further on, because we have got a section to talk more about that. But this metal here could be copper, could be zinc, could be magnesium, could be calcium, could be iron, okay? So that is the electrode. In the same way, we've got an electrode here. Okay, so this is also an electrode. Right. This part here is very important. This part here that goes from one solution to the other. This part here. Now this part, made of a U-tube, is called the salt bridge. Okay? Salt bridge. Now the fact that it is called the salt bridge, it is because inside of it, it contains a salt solution. So inside there, we've got a salt solution. Now if you remember well, salts are mainly ionic. In other words, inside there we've got positive and negative ions as well. So inside here, we've got an ionic salt solution. Okay, now, out here, this is just a connector. You can see made of wire. It could be a copper wire. That's a connector. That's a voltmeter. Okay, so we can say this is a voltmeter. And we usually, instead of voltmeter, we usually use what we call a galvanometer. Why a galvanometer used instead of a voltmeter? Because the voltage as produced by this cell is very small. So it is always better to use a galvanometer to measure the amount of energy, potential energy that comes from this cell here, because the voltmeter will need large energy to be coming out in order to work much better for us to see any deflection of the needle. So we normally use a galvanometer, but of course a voltmeter could be used. Now, so we have this, and you would see that the external part from here to there is actually wires, electrical equipment, and we call this the external circuit of the galvanic cell, or of our cell there. We call it the external circuit. Okay, and we're going to explain further about this galvanic cell and of course the electrolytic cell as we move on. But this is basically the general idea or the general knowledge that we need to know about galvanic cells. The structure, what are the different pieces called, what happens inside them. But most of the content, most of the ideas about what happens inside, we're going to look at as we move on. Now let's have a look at the electrolytic cell. Okay, now there is an electrolytic cell. Now look at the difference now. Instead of a voltmeter or galvanometer there, what do you see? What do we have there? We have got a cell, and it could be, of course, a battery. Remember the difference between cell and battery? A battery is it's made up of a number of cells connected together in series. So that could be a cell or a battery. And of course, the long arm here represents the positive side or the positive terminal of the cell, and that represents the negative terminal of the cell. Hence, we have got the negative here and the positive there. This negative and the positive is not as a result of what happens inside the solution, but it's only as a result of the connection of the cell or the battery, because the terminals would stay as they are. Now, what are these? What do we call these two? Remember what we called them earlier on? We call them electrodes. So these are electrodes. Okay? Now these electrodes here could be made up of metals, they could be made up of graphite, okay? Depending on what is the purpose of this cell. Now, in the same way with a galvanic cell, this part here, this section here, it's a container with a solution. It's an ionic solution, okay? Now, this is a solution that can conduct electricity. And what do we call a solution that can conduct electricity? We call it an electrolyte. Electrolyte. Okay? Electrolyte. A solution that can conduct electricity. It's a solution that can conduct electricity. Okay? Now, let's look at something else in comparison to the galvanic cell that we looked at earlier on. If you check here, like I said, we've got a cell, we've got a battery, and we know that the battery provides energy. It provides electrical energy. So electrical energy is provided to or into this cell here. Okay? Now, what does this electrical energy do, and where does it go to? This electrical energy goes into the solution there. You may not be able to see that color that well, but it's energy that is coming into that solution there. This is the energy provided by that battery or the cell, and it is made to do some work there. So in this case, we have got a situation where the electrical energy, okay, electrical energy is converted into chemical energy. Okay, so now we've got that difference there, as you see, as compared to a galvanic cell. Because remember, with galvanic cell, we said when we looked at the structure, it could tell us that the chemicals inside the two solutions were actually providing or generating that electrical energy. But this case, we've got battery outside, in the outside circuit, providing the energy into the solution or into the chemicals inside. And due to this energy that is sent or provided into these chemicals in here, something happens inside here. And that this happening is due to the electrical energy pushed into that solution. So the electrical energy does some work there. The electrical energy is now converted into chemical energy inside there, causes that chemical reaction, some chemical reaction in there to occur or to take place. So that is basically, in general, the two cells, the galvanic cell and the electrolytic cell. And we're going to talk more about this. Like I said, this is just the basic information that you need to remember every time we look at these two. Now, here we are. We want now to look at in details into what we call a galvanic cell. Okay, now, galvanic cell, we are going to specifically look at that one of zinc-copper. All right. Now, let's explain this. Zinc-copper. This would mean that one side of our cell is zinc and the other side is copper. It's made up of copper. Now, let's look at it. If one side is zinc, then inside here, we're going to have a zinc solution. Okay? So zinc solution. So this side, we're going to have copper solution, Cu solution. Allow me to abbreviate it for the sake of space. Copper solution. All right? We know what this is the salt bridge. And what we also need to understand about the salt bridge is that inside the salt bridge, we have a saturated solution. Saturated solution. And of course, ionic solution. Now, what is a saturated solution? Now, a saturated solution is a solution that cannot take more of the solute. The capacity to take the solute, to dissolve the solute in it, has been exhausted. So even if you put more of whatever you were dissolving, it's not going to dissolve, it's going to stay as solid as it is, or as in its own form. Okay, so it's a saturated solution. And of course, an ionic solution. And then, that side, okay, we've got a copper solution. It would mean that this electrode is therefore an electrode of copper. All right? In the same way here, we've got a zinc solution on the left side. So this electrode here will be an electrode of zinc. Okay? Zinc metal made of zinc. And when we say we've got zinc solution, what do we mean? We mean that in here, they are the zinc plus ions. In the same way, when we say we've got a copper solution inside this, we've got a copper solution here in this cell, or this part of the copper or the zinc copper cell, it will mean that inside here, or this solution here, contains the Cu2 plus ions, or the copper ions. Okay. Now, when this chemical cell, this electrochemical cell called galvanic cell is in operation, there are chemical reactions taking place on both sides of the cell. In other words, on the one side where we've got the zinc, also on the other side where we have copper. Let's try and look or get deeper into it, check what type of chemical reactions are taking place there. Now, on the side of zinc, you would remember that we've got the zinc electrode, right? So Zn. What happens there is that the zinc is seen, or it has been observed, to be losing electrons and forming the zinc ions. And those electrons that are lost by each one of the atoms of zinc are 2. So one atom of zinc will lose 2 electrons. So this is the process happening on the zinc electrode. The zinc solid neutral loses electrons to become zinc 2 plus ions, and there are the electrons that are lost. Now, what did we say losing of electrons is all about? Losing of electrons is called oxidation. So we see zinc here undergoing oxidation, all right? And as those electrons are being lost, where do they go, all right? What we see happening here is that we have a conductor here, up here. This is an electrical conductor. The electrons that are lost by zinc get onto this wire and move in that direction. So that is how the electricity is generated. Now another question will be to say, where does the zinc ion go? The zinc ion, the Zn2 plus, goes into the solution. So it starts from there, it loses electron, say that is an atom of zinc, it loses electrons, it becomes Zn2 plus, then it gets into this solution, Zn2 plus. And those lost electrons, the lost electrons move up that way into the external circuit. That is the direction that electrons will take. Okay, so what basically is happening here in terms of the Zn2 plus ions, okay? The Zn2 plus ions are increasing all the time. As oxidation takes place, we're having more and more of the Zn2 plus ions getting into this solution. In other words, the concentration of the Zn2 plus ions increases. So we'll say that concentration of Zn2 plus ions in that solution increases. Okay, so that is what we're seeing happening there. On the other side as well, let's check what is happening. Here, those electrons, remember they are moving through the external circuit. They are moving. That's the direction that these electrons are taking from zinc. There they go. Okay? And these electrons get into the copper solution. Okay? Now, upon reaching that point, what happens with those electrons? Now, let's look at what happens with those electrons quickly. Okay, now, this side of the electrochemical cell, remember what we have. We have the copper ions in solution. They are positively charged, and electrons are negatively charged. Now, negative and positive we know will attract each other. What happens here is that this copper 2 plus ions says, well, electrons, here we are ready to receive you. And they receive those electrons, the copper ions, and become copper solid. Okay, this will be solid copper formed on that electrode there. Okay, so this is basically what is happening. And what we call a process where electrons are received, we call that reduction. So reduction happens or occurs on the copper side. The copper ions are reduced to copper solids or copper atoms. Okay, so that is what we are seeing happening there. Now, let's try and check here. Let's try and look at these two terms here. Remember the two terms we looked at when we started: reducing agent and oxidizing agent. Okay? And we said that the reducing agent is the substance that donates or loses electrons. Now, which one between the copper ions and zinc here is giving away electrons? You will see that it is zinc that is giving away electrons. Oxidizing agent, we said this one is a substance that receives the electrons. Which one is receiving the electrons? Is copper 2 plus. Now, be very careful. You can't say copper is the reducing agent, because it is not copper that is taking the electrons, but it's copper 2+. It's the copper ions that are taking up the electrons. Reducing agent is, of course, zinc, because that is where the electrons are lost. Okay, so we can use this to explain further the terminology that we started with. Let's continue to check more on what is happening into these cells here. Remember, on the zinc side, we said the concentration of the zinc 2+ ions increases. All right? It increases because every time a zinc atom is oxidized, a zinc ion, a Zn2+ ion, gets into that solution. But then what is happening here? Every time electrons arrive there on this electrode, what happens to the Cu2+ ions? The Cu2+ ions are taken out of the solution. So the concentration of the Cu2+ ions decreases. Okay? So we see that the concentration of the Cu2+ ions decreases. Now, experimentally, we can see this because we know that these Cu+ ions are blue in color, right? This blue color sort of fades over time when this cell is in operation. What does the fading explain to us? It tells us that more and more of the Cu2+ in this solution, the Cu2+ in this solution, are taken out of solution and becoming copper. And what will be happening as the Cu2+ is receiving electrons and becoming copper and sticking on this electrode here, on this copper electrode? What we'll see happening is a build-up. There is going to be a build-up of copper around this electrode there. So this electrode here is going to increase in mass. Let's write that down again as well. So we see copper electrode increasing in mass. Increasing in mass because more and more copper is formed and deposited around it. Copper electrode increases in mass. It increases in mass. Okay, so because the copper is deposited around the copper electrode there. In the same way, we can try and explain what is happening on the side of zinc. Remember, there is an electron here, there's an atom of zinc there. It gives away an electron, it gets into solution as Zn2+, zinc ion. The same thing happens. So your atoms of zinc are getting smaller and smaller and smaller, okay, on this zinc metal here. So in other words, this zinc metal is eroded. It's getting smaller and smaller and smaller. It can actually get finished over time. So what do we say about the mass of zinc? On the other side, the zinc mass decreases. So we're seeing the mass of zinc decreasing because that is where oxidation is happening. More and more of the zinc atoms are becoming zinc ions into solution. Unfortunately, the zinc ions are colorless, so we can't see any intense color forming because they are colorless. Even if we can have more and more of them coming into solution, their color will remain as it is. It will be transparent, colorless, so we won't see any change in color. But the fact is, as more and more atoms of zinc get oxidized, the mass of the zinc gets less and less, and therefore the concentration of zinc increases there, as we have explained earlier on. So that is what we see happening here. Now, let's check on what we're seeing here. Remember that electrons are moving this side. And because they are moving from the zinc in that direction, this part here is negative, all right? And it is negative, and that side, most of the copper ions are actually clinging onto the copper electrode, thereby making this side to be positive. Hence, electrons are able to move from the negative to the positive. Okay? And so that is what is happening here. Right now, at the beginning, we defined two very important terms as well. And these are, one, the anode. Okay? So we also spoke of the anode. How did we define the anode? We said that the anode is an electrode where oxidation occurs. Electrode where oxidation occurs. Okay? All right. And where does oxidation occur in our electrochemical cell here? In other words, where do we see the loss of electrons? You would see that we see the loss of electrons here on zinc. That's where we're seeing the loss of electrons. And therefore, this is then our anode. So we can, of course, then label it as the anode here. Can say that this electrode is the anode. Okay? That color is not so clear there, but the anode is the zinc electrode in this case. Why? Because that is where oxidation is taking place. Now let's look on the other side. We also defined this other term, the cathode. And we said cathode electrode where reduction takes place. Electrode where reduction takes place. Now, where did we see reduction taking place or occurring? We saw reduction taking place on the copper electrode. This is where reduction is taking place. This is where we're seeing copper being formed there, the Cu2 plus ions gaining electrons and forming a mass of copper on that copper electrode. So this one becomes our cathode. So this copper electrode is the cathode. Okay. Now, I want us to look at something very important here in terms of anode and cathode. Because we have to also look at electrolytic cells, we need to define it in another way as well. Now, when we look at the electrochemical cell in here, we said inside here we have got chemicals. Say we have got a chemical or a solution of potassium nitrate that is inside the salt bridge. This means that we have got K plus ions and NO3 minus ions. Now, where are these ions going? Okay? Now, remember that you are, from the zinc side, we're having a lot of the Zn plus ions getting into solution. So you've got more and more of them coming in here. These are the Zn2 plus. Do you think the plus will be wanting to come down here? No, because plus and plus will be repelling each other. There will be a build-up of the pluses here. Now, what is going to happen to the pluses there? The pluses would want to be associated with the minuses that are here this side. So we see the K plus ions moving in that direction. In the same way, the buildup of the 2 plus ions here, the zinc 2 plus ions here, makes this part to be more positive, and then this one, this negative NO3 ions would want to come this way because they are attracted to the Zn2 plus ions that are here. Okay, and what is the duty of this salt bridge? It is to maintain the neutrality of this cell. When you pump one Zn2 plus ion into this solution, one NO3 or 2 NO3 ions there, because this one is Zn2 plus here, one NO3 ion is carrying 1 plus. So 2 of this will come this side to neutralize the increase in the 2 plus charges there. In the same way here, when the plus charges, 1 2 plus charge of copper is gone this side, 2 of the K plus ions here will want to go in there and take the place of the Cu2 plus ion that has been taken out of solution. Okay, so that the electrical neutrality is happening. Now, let's look at it. the negative ions are moving from the salt bridge to this electrode, to the side of this electrode. So the electrode to which the negative ions move to will be called the anode. And the electrode where the cations, the positive ions, are moving into will be called the cathode. Now you can see N ions, okay? N ions, which is the NO3 ions in this case from the salt bridge, are going this side. N ions are going this side. And we call this electrode the anode. Okay? On the right-hand side, cations, positive ions, we call positive ions cations. Cations, the positive ions, are going into that direction. And because they are going into this electrode, we will call this the cathode. So you can see that the N ion is from the fact, or the anode, the N is from the fact that the N ions are going there. The cathode, the cat is from the fact that the cations are going that side. So this is another way that you have to look at this. And it is very important because when we look at the electrolytic cell, people begin to get confused because it sort of differs from what we start with when we look at galvanic cells. But really, there isn't much difference. And then this side is negative, that side is positive. Okay. Right, we looked at the copper zinc or the zinc-copper galvanic cell. And suppose we remove the external circuit and we remove the salt bridge. In fact, or everything that connects them together. And let's see what happens. What we are remaining with will be the cells like this. For example, we would be having the zinc cell. And we call it the zinc half cell because it's just 1/2 of the whole cell. So this will be the zinc half cell. And remember that this is where oxidation happened. But because this time this thing is not connected to any other cell, it looks like nothing is happening and we may not necessarily have the voltage or potential difference created. But let's look deeply into what is happening inside here. We know that here we have got a solution of zinc 2+, and this is a zinc electrode. Okay, so this is what we have. Actually, in chemical terms, something is happening here. There is a reaction inside this solution here, okay, between the zinc electrode and the solution. And what is that reaction all about? The reaction that is happening there is such that when this zinc electrode loses electrons, okay, the 2 electrons are received by the zinc 2+ ions in the solution, okay, to give us the zinc atoms. But at the same time, we have got the zinc atoms losing electrons to give us the zinc 2+ ions. Okay? And these two processes happen at the same time, and the rate at which they happen is the same. So equal rates, how fast the first happen, so how fast one occurs equals to how fast 2 occurs. And because of that, we've got a situation where we don't necessarily have to rewrite 2 there. We have got an equilibrium, if you like. So this is a reversible reaction. That is what we are having. And because the rate at which zinc 2+ is receiving electrons to give us zinc, and zinc atoms are losing electrons to give us Zn2+ is the same, because that rate is the same, we have got a state of equilibrium, and it looks as if nothing is happening there, but basically something is happening. In the same way, we can look at the copper half cell. Okay, there is our copper half cell. We call it a half cell because it's just half of what we had together when we had a full cell. We have got the Cu2+ ions there. We have got the Cu electrode. And exactly what I explained up there is what is happening here. Cu2+ plus 2 electrons. Okay, in equilibrium, we're getting the copper solid there in that way. So it looks like as if nothing is happening. But if you can check carefully, these two equations here that I have just shown you are the equations that you see in your table of standard reduction potentials. So this is actually where it comes from. Now, let's move on. Let's now go to the standard hydrogen half cell. Now, what is this? What was this for? Look, we said that the zinc-copper chemical cell is generating electricity. It is producing electrical energy, okay? Then the question is, can we determine how much of that electrical energy is there? Can we calculate the voltage, the EMF of that cell? Can we find it? All right? And then we had to find a way to be able to find that, because basically by looking at the zinc copper cell, we will see it generating electricity, but we wouldn't have means and ways of finding exactly how much of the potential difference is being created there by the cell. Okay, now let's look at how this was found out. We make use of what we call the standard hydrogen half cell. And when we make use of this standard hydrogen half cell, the word standard, it is formed or created under standard conditions. And what are these standard conditions? We should be having a temperature of 25 degrees Celsius, which is 298 in Kelvin. We would make sure that the pressure of the air around there is 101.3 kilopascals, or 1 atmospheres. And the concentration of each of the solutions should be 1 mole per cubic decimeter. In this way, we have a standard half cell. Now, the temperature will definitely apply to every type of a half cell. This one will only apply when we're talking gases, in other words, substances that are in a gaseous form. This one will apply, of course, to all. We have a concentration of air. We can be able to calculate that. We can have concentration of solutions. So this is what we need to bear in mind every time we talk about these standard conditions. Some of them are not applicable to every particular cell. Now, the standard hydrogen half cell is what we call our reference point. Okay, so we want to try and find out the potential of the others. And by making the standard hydrogen half cell to be our reference point, we assign a value of 0.00 volts. In other words, even if it is producing some potential difference, we say let it be 0, so that we can measure the others against it. So if we connect it to a zinc half cell and the voltmeter gives us a reading, we'll say that reading is for zinc because our standard hydrogen half cell is assigned a value of 0.00 volts. Okay, so what is that half cell? The standard hydrogen half cell, that is the cell, and that is the E cell. We call it the E0 cell, not for conditions, for the standard conditions. So it will be 0.0 volts. And from this, every other EMF was found. And that resulted in this table here. You would see, if we come to the middle here, although you may not be able to see this very clearly, this print is quite small, we have the standard hydrogen half cell there. And every other E cell for the half cell you see there is the voltage given out by that cell when you have got this cell connected to this half cell connected to the copper half cell. If the voltage under standard conditions was found to be 0.34, and all of it was assigned to the copper half cell because this one is taken to be 0. And in that way, every other half cell was found. The E0 for every other half cell was found in the same way. So above the hydrogen half cell, you'll see we have got the negative values, and below it we have the positive values. This side, it says increasing reducing ability. Now we have got an equation here, all right? This is the equal sign of the equation, and we have got PB there on the right-hand side. Increasing ability refers to these entities here. So their reducing ability increases as you go up the table. So this means that magnesium is more able to reduce than lead. In other words, magnesium is more readily able to lose electrons. More able to lose, okay? More able to lose than lead. Lead can lose, but in the presence of magnesium, magnesium will be the first one to lose, not lead. Right, on the other side, we've got increasing oxidizing ability, and that increases as you go down the table. And this would mean that magnesium 2 plus there, if we compare it to lead 2 plus there, for example, would see that lead 2 plus is more able to oxidize, in other words, to cause other substances to lose electrons, okay? So as compared to magnesium 2 plus. So magnesium 2 plus is less able to oxidize compared to lead 2 plus. Okay, and then we will be using this table a lot as we move on and being able to calculate for the E cells or the EMF of the cell, okay, under standard conditions, of course. Right, so that is basically the table. Now, let's look at an example. We've been talking and talking a lot. Let's see if we can approach some of the questions and answer them. Two pairs of half cells are used to set up galvanic cells, A and B. So cell A consists of calcium and lead half cells. Cell B is of aluminium and magnesium half cells. Use the table of standard reduction potentials to answer the following questions about A and B. Okay? Now identify the cathode. Now let's look at A and B. Now what is A? A is calcium and lead. Okay? We need to identify what will be the cathode, what will be the anode there. From the table of standard potentials here, we've got, there is the calcium level, okay? And the other part is that of lead. So we've got calcium there, we've got lead down here. Okay, so there is lead. All right, and let's get the others as well quickly so that we don't waste time. We've got aluminium and magnesium. So let's use a different color for magnesium and aluminium. So there is magnesium there, and there is aluminium. Okay, so this is our cell 1 or A. A there. This is A, sorry, that's A, and this is B, and that is B. Right, let's answer these questions. We have calcium and lead for A, okay? And we have to identify the cathode and the anode. Remember the cathode, that is where reduction happens, the electrode where reduction happens, anode, the electrode where oxidation happens. So for A, we see from the table of standard electrodes, potentials, okay, that calcium here, all right, remember this is increasing reducing ability. So calcium will be more able to reduce than lead when they are put together. So calcium is going to give away electrons, and then lead ions are going to receive them. So because it is calcium that is going to lose electrons, calcium electrode is going to be the anode. So calcium is our anode here, okay, for A. And then lead, allow me to just write Pb for now. Lead will be the cathode, okay? That is where reduction is going to take place. On the other side, we've got aluminium and magnesium, okay? Magnesium is more able to reduce. Magnesium is more able to reduce. Why? Because look at magnesium there, increasing, reducing ability compared to aluminium there. So magnesium is going to be the one that is going to lose electrons. So because magnesium will be the one that is going to lose electrons, would have for B, magnesium Mg being the anode, and then aluminium being the cathode. That's where reduction is going to take place. Okay, now next question. What are the oxidizing and reducing agent? Now we can quickly get it from here. Calcium anode, because that is where reduction, that's where oxidation is taking place. So we would say that calcium Ca for A, because this is the one that loses electrons, this will be our reducing agent. And therefore, what will be the oxidizing agent? Now I said in our explanation that be careful. It's not Pb that is the reducing, oxidizing agent, but it is the ion of Pb, ion of lead, which is Pb2+. This will be the oxidizing agent. Okay? So that's how it will be for A. For B, how is it going to be like? Magnesium is the anode giving away the electrons. So that will be the reducing agent. Mg, reducing agent. Reducing agent. And then Al, remember, is it Al? No, it will be Al3+. Remember, it's going to be 3+ with the Al. Al3+ will be the oxidizing agent. Okay, oxidizing agent. So we've answered that question now. Now write down the oxidation and reduction half reactions. Okay, for A, okay, we know that for A, calcium is going to lose electrons. The half reaction will be such that calcium from solid, from being an atom, it forms the 2+ ions and gives away the 2 electrons. The lead, okay, will be the reduction half reaction. It will be the Pb 2+ plus 2 electrons, and that gives us the lead solid. Okay, so that will be the oxidation half reaction, and this will be the reduction half reaction. Okay, and then for B, in the same way, magnesium gives away electrons, so oxidation. Magnesium gives away electrons, magnesium 2+ plus 2 electrons, and that is your oxidation. The next one, aluminium 3+ gains the electrons, becomes aluminium solid, and that is the reduction. Okay, so we've written that, we've answered that. 1.4, write down the overall cell reaction. Now, let's start with A. Take it from there. Now, you see you've got CAS. So, overall cell reaction, you put the two together. You put these together. So, I've got Ca solid, everything on the left side. So, plus Pb 2+. But hey, the 2- on the left side and the 2- on the right-hand side cancel out each other. So this we know it is in solution AQ. Then the final on the other side, because the 2 E's are gone, I've got Ca2+, That's getting into solution. And I've got the last one, which is Pb, taken out of solution to be a solid. Okay. For the B section, in the same way, I've got magnesium on the left, solid, of course. Let me put the state here, solid, plus Al, 3 plus, it is in solution. All right. Now, we need to be careful here. We've got magnesium with 2 plus there, and then it's losing 2 electrons, okay? And then we've got aluminum, it needs 2 electrons. It needs 3 electrons. So we need to be careful. What we do is we need to balance the number of electrons. So we multiply this one by 3, okay, which is this 3 here. And we're going to multiply the reduction half reaction by 2, which is that 2 there. So we balance the electron values. So when we multiply the top by 3, we've got 3 there, and that will be 3, and that will be 6. And when we multiply this one by 2, this will be 2, and this will be 6, and that will be 2. So when we write down the final answer here, we will have, you would see here, would have 2, it's what? It's 3 mgs, okay? 3 of the Mg, magnesium, and then we have got 2 aluminium. That will give us, and remember the 6 and the 6 electrons are going to cancel out because they are on either side of the equations, and then we're going to have the 2 aluminium solid plus, what is that? The 3 magnesium ions, 2 plus ions. So we have got 3 there. We have got the 2 here. We've got 2 there, and we've got the 3 there. Now that's how we write this, the net cell reaction for B. 1.5, write down the cell notation. Now this is very important. We need to learn to do our cell notation. Cell notation, we just show from left to right, and I'll be explaining everything I write here. Look at it. When you start with calcium, it's Ca, this is for A, and it ends up as Ca2 plus. So we would say Ca starts as Ca solid, it ends up, this is a slash, it ends up as Ca2 plus, okay, in solution. So this is the first part. This is the oxidation part. You start with the oxidation part and end up with the reduction part. In here, we use the double arrow, and the double arrow is a symbol for our salt bridge, right? And then we show what happens on the reduction side. We start with the oxidation, we end with the reduction side. The reduction side, we see Pb starting as Pb2 plus in solution and ending up as Pb solid. Okay, so that is called the cell notation. Remember, you start with the oxidation side and end up with the reduction side. You show the state in which your substances are found, solid, aqueous. You show the charge if it's ions, and the double slash there for your salt bridge. Okay, now let's move on. Calculate the EMF. Let's start with A. Okay, the EMF is found in this way. E cell, E naught cell is always given by E naught cathode minus E naught anode. Okay, now this then for A, it's going to be, now what was our anode? Okay, for A. For A, our anode was our anode was calcium, because calcium is the side where reduction is taking place. So let's look at calcium in our table here. Now, calcium minus 2.8, that is our anode. Lead it's our cathode, okay, minus 0.13, okay, 287 and 0.13. Okay, let's see. Okay, so for here the cathode is minus 0.13. Remember, it's the lead. Minus E anode minus 2.83. Must confirm this. That is 2.87 for calcium. Okay, so there we go, 2.87 minus 2.87. 2.87. Now, what is this going to give us? This will be minus 0.13 plus 2.87. What will be the answer? 7 minus 3 will be 4. 8 minus 1 will be 7. 2 minus 0 will be 2. Okay, so we're going to have 2.74 volts. So that will be the EMF of A. EMF of B, I'm not going to write the formula again because we have it now. It is going to be E cathode minus E anode. What is our cathode here between aluminium and magnesium? Magnesium will be the anode, aluminium will be the cathode. 1.66, 2.36. 1.66, 2.36, right? Okay, so E cathode minus 1.66 minus 2.36. 2.36. Okay, 2.36. This is going to give us minus 1.66 plus 2.36, and the answer here is 6 minus 6, 0. 3 minus 6, no, then 13 minus 6, it's 7. 1 minus 1 is 0, so 0.70 volts. This will be the E cell of B, right? So that's how you work out your EMF of the cell. Now, let's move on quickly to talk about equilibrium in galvanic cells. Now, when it's a state of equilibrium reached in a galvanic cell, it is reached at this point where you've got 0 volts. Okay, the galvanic cell cannot give you any more electrical energy. Let's try and explain this. Remember, in the zinc half cell, you have got a situation where oxidation takes place. So more and more of the zinc 2 plus ions are getting into solution, whereas on this side, you're starting with many of those Cu2 plus ions in solution. But reduction takes place here such that as the cell continues to operate, these ions are going. They're getting less and less and less. So there would be a situation where you've got too much of this in and less of that. But what happens, remember, is that you've got the salt bridge here with a salt solution, okay? Some of these ions are going that direction. Do you remember which ones are those? The plus is going there, and the negative is going that side. Okay, now there would be a situation where as much of these ions get into solution, we have got as much of that going out of solution. So that situation, when that situation comes, we have a state of equilibrium. So if we look at the concentration of the zinc ions, for example, let's look at the concentration of zinc ions. Zinc ions and copper ions. So say this part here, the bottom part represent the concentration of our copper ions, and the top part represent the concentration of our zinc ions there. Okay? What happens over the time? Over the time, with the copper ions, we see them getting less and less from the solution, taken out of the solution. Now from there to there, nothing is happening, because at that point, perhaps, let's say this is your T1, no reaction is taking place, the cell is not in operation. But from T1 upwards, the cell begins to operate, and then we see the zinc ions getting more and more there up to that point, okay? Whilst the copper ions getting less and less up to that point. Now, let's look at what is happening. At that point, we see that the concentration of copper ions and concentration of zinc ions sort of level up, remains the same. From T2, let's call this one T2, until the end there, let's call that T3. What has happened? At this point, a state of equilibrium has been reached. You have reached a state of equilibrium such that as much of this gets into solution, we have got as much of that coming out of solution, and there is no voltage happening there. A state of equilibrium has been reached. So that is how the concentration of cations changes inside your galvanic cell, and a state of equilibrium is reached. Let's now quickly move on to talk about electrolytic cell. An electrolytic cell, like we said earlier on, you would remember that we said here we've got a cell or a battery, okay, and that supplies energy into the cell. And then you've got ionic solution there. Because this electrode is made positive by the battery, the negative ions move into that. The positive ions would move into this electrode because it has been made negative by the battery there. Now, what is going to happen here? This molecule, which is negative, is going to lose electrons here. When it loses electrons here, and electrons goes up there, remember the electrode where oxidation happens is called we call it the anode. So that becomes your anode. You would see now that it's not the same, that the polarity is not the same as the galvanic cell. This one, on the other hand, okay, this is where reduction happens. Here, reduction is going to happen. The electrons are going to come in here, okay, and then be received here by those ions there. So reduction happens here. Reduction is happening this side, and because reduction happens this side, we will call this electrode, we will call it the cathode. Don't have much space here to write on. Allow me to just write cathode like that. Okay, so that will be the cathode. And so that's how your electrolytic works, electrolytic cell works. Now, if electroplating is to be done here, because this is mainly where the cell is used. It's used in electroplating. You know, your copper metals made to look like gold or silver, and then we say, yes, I've got a gold watch. I've got some of those things are not necessarily gold, but coated with gold. That is electroplating. So in that way, if it is to be electroplated, that thing will have to be, remember, reduction happens here. So we'll have the deposit of whatever has been reduced on there, okay? So on the cathode side. Let's quickly go to an example for this. Example 2. This comes from the National Senior Certificate Exam, March 2009, paper 2, okay? An attractive silver appearance can be created by electroplating artifacts made from cheaper metals such as nickel with silver, okay? The simplified diagram below represents an arrangement that can be used to electroplate nickel with silver. So here is nickel, an artifact made of nickel. it should be electroplated with silver. There is electrode Y there. Okay. Electrolyte containing silver ions. So we have got Ag plus ions in this solution. The question is, which electrode, cathode or anode, will the nickel artifact represent? Okay? Is this the electrode where the silver ions will go to so that they can be reduced should be the cathode. So the artifact should be on the cathode side. So that will be our anode. Okay? Right. And 3.2, name the metal represented by electrode Y. Okay? So what metal represent electrode Y? For us to make sure that there is enough Ag plus ions in solution, this electrode must be a silver electrode. So this electrode must be made up of silver. Okay, so that metal is silver. Right. So the answer there is cathode, and the answer here is silver. That's the metal for Y. Write down the half reaction responsible for the change that occurs on the surface of the artifact. What happens there, we've got silver ions in solution receiving electrons, becoming silver and getting coated around that nickel artifact. Okay. Give a reason why the concentration of the electrolyte remains constant, okay, during the electroplating. As Ag2 plus, as the Ag plus ions, as the Ag plus ions get reduced to Ag, silver. Okay? Ag atoms from the Ag electrode, silver electrode, get oxidized in the same rate. They get oxidized to Ag plus. So the concentration of silver here, of the electrolyte, Ag plus, remains constant in that way. Okay, so that's the reason why. In industry, some plastic articles are sometimes electroplated. Explain why plastic must be coated with graphite before electroplating. Because plastic is not a good conductor of electricity, okay, whilst graphite can. So plastic is not a good conductor of electricity. You can actually say that plastic is an insulator, okay, doesn't conduct electricity that well. That's why we can't use it as it is. Give a reason why, from a business point of view, it is not advisable to plate platinum with silver. Wow, can you really plate platinum with silver? No, because platinum is more expensive. Platinum is more expensive than silver. So this is from a business point of view, it is really unnecessary to use platinum there, because you can actually sell platinum at better prices for something else than coating it with silver to make artifacts look nice. Otherwise, that brings us to the end of this session. I hope you enjoyed the lesson. Thank you so much for watching. Till we meet again, my name is Tinyiko Kosa. Keep well.